discussion of linear algebra, we'll frequently see certain kind of matrices. In this lesson, we quickly review those matrices and further refresh our memory on determinant. We'll not discuss determinant in detail, and I assume you have already studied determinant thoroughly. It would be very helpful if you can go back to your mathematics textbook and review the determinant. We are already familiar with matrix transpose, where row and columns of a matrix are interchanged. We have also learned symmetric and skew-symmetric matrices. In the first case, the matrix is same as transpose, while for the second, matrix is the negative of the transpose. We also know that for a null matrix, all the elements are zeros. In this course, we will mostly deal with square matrices, and we will see several interesting structures in the square matrices. First one is the diagonal matrix, where non-zero elements stays in diagonal only. The identity or unit matrix is a special kind of diagonal matrix where all the diagonal elements are 1. In upper triangular matrix, all elements below or left of the diagonal are 0, while in the lower triangular matrix, all the elements above or right of the diagonal is 0. A special square matrix that often helps us a lot in solving linear equations is the permutation matrix. In permutation matrix, each row as well as each column contains exactly 1, 1. All other elements in the permutation matrix are zeros. Identity matrix is certainly a special form of permutation matrix. In general, permutation matrix comes from exchanging the rows of identity matrix. It is interesting to see what permutation matrix does. To start with, we can see what an identity matrix does. When I matrix is multiplied with another matrix A, we find that the product is still matrix A. So the multiplication with I matrix does not make any difference at all. Now when we multiply A with the permutation matrix P, that is 0, 1, 1, 0, the row 1 of the product is 0 times the top row of A plus 1 times the bottom row of A. Thus you can clearly see that the rows have been exchanged. So whenever we wish to exchange rows of a matrix, we multiply the matrix with an appropriate permutation matrix. Let us now have a quick review of determinant. A determinant is a scalar that provides some sort of a magnitude of a square matrix. For a matrix with one element, determinant is simply the value of that particular element. If we wish to find the determinant of a general n by n matrix, where n is greater than 1, first we look at the minor. The minor Mij is the determinant of B matrix. The B matrix is an n-1 by n-1 matrix. The B matrix is formed by removing the ith row and jth column from the matrix A. Once we find a minor Mij, we form the corresponding cofactor Cij. Cij is Mij multiplied by -1 to the power I plus j. Once we have all the cofactors ready for all elements in a particular row of a matrix, we can find the determinant as the sum of Aij into Cij for any given row. A matrix with zero determinant has special importance in linear algebra Such a matrix is called singular. Every non-singular matrix A has an inverse, denoted as A to the power minus 1, such that when A and its inverse are multiplied, we get the identity matrix. For any matrix A, the multiplication of A inverse with the determinant of A produces a cofactor matrix. Every element of the cofactor matrix is the cofactorCij's of matrix A. Although we will not go through the detailed derivation, I encourage you to prove this expression of inverse. While matrix inverse is extremely useful, especially while solving linear equation, finding matrix inverse using the above expression is exceedingly difficult. The difficulty comes from the fact that finding the determinant of a large matrix is a prohibitive task even with a high-speed computer. In the upcoming lessons, we'll see how we can find inverse using some intelligent elimination technique. Of course, before we go there, we will discuss the connection between matrices and the elimination techniques. So for now, please go back to your textbook and solve problems from the relevant chapters, especially from determinants. In this course, we will not talk about determinants anymore. Study the determinant section from your textbook, including the Cramer's rule, which is a technique for solving linear equations using determinants. So that's all for this lecture. Thank you, and I'll see you in next class.